Hi, everybody. Thanks for coming to today's webinar. My name is Debbie Penko, as Amber mentioned, and today we'll be doing foundation design, focusing on retaining walls. First of all, let's see here. Everybody should see my screen, and I'm just going to go to the next slide here. The version of the software we're talking about is RISAFoundation version 4.0. So we recently released that. We also released RISA-3D version 10.0 and RISAFloor version 6.0. So these three programs actually integrate with each other. So when one gets released, they all get released so they can speak together. And so some of the things we'll actually introduce in RISAFloor and RISA-3D to get into RISAFoundation so we can see some of that integration. But we'll be focusing on version 4.0 of RISAFoundation. Some of the things that were added into RISAFoundation and the newer features will be the retaining walls. This is a big thing we're going to be talking about mostly on this presentation. But I do like to point out some of the other things that we added in this version. So we added a lot of newer codes. So you'll see some of the ACI codes for the concrete. We'll have Canadian as well as Saudi design codes have been added into the new versions. You also have got we've optimized footings for uplift, overturning, and sliding. So those are features that we always had uplift, overturning, and sliding, but the newest part is we're optimizing that footing there for those. So that's a nice new addition to the program. But what we want to kind of learn a little bit more about is retaining walls. This is a really big feature, and there's a lot to it. So hopefully this hour-long presentation will give you a lot more in-depth information about it. And we see here on the right, that's a screenshot of what the input looks like, and we'll get a little bit farther into the input as we go. But I want to kind of focus on some of the features here that got added into it. The soil loading, the input, when we see we're going to put some input in here for soil, and automatically the program's going to calculate our soil loads, as well as take exterior loads. So any kind of line loads or point loads that we put on the retaining wall are also going to be carried into that retaining wall. We also see that we can do cantilevered or supported walls. A lot of times I'm going to call supported walls as propped walls. That'll be sort of the same thing as if a slab or a diaphragm was tying into the top of a retaining wall, which we would call a supported wall. We also added stem wall and footing wall design for this retaining wall. So we're going to design the concrete for the stem wall and for the footing. We're also going to do overturning and sliding checks for that retaining wall. We're going to do see the loading diagrams. So broken into, for the detail report, we'll see that the loading diagram is described for the retaining wall. In that detail report, we'll also see axial, shear, and moment diagrams describing what's happening along that wall. And lastly, we'll see the reinforcement design. So these are kind of a quick breakdown, but this is a nice overview of what we'll be reviewing in this presentation. So as I go forward here, let's talk a little bit more about the soil. If we look at this retaining wall, and this retaining wall is going to be something we're going to lay out in RISAFoundation, and it's got sort of three regions. The regions for the soil here are underneath the toe. Also here we've got the heel portion, and then we also have a saturated heel portion. So wherever your water height lies, that's where our retaining wall hits there. For that, we're going to calculate a lot of different things here. So we're going to actually ask for input of the coefficient of internal friction and backfill angle, and then the K will be calculated for you. So here this shows us how this K is going to be calculated. This lateral force coefficient is going to be calculated. And if we are using, we're using actually the Rankine theory right there, based on the Rankine theory. And the theory there, we're assuming that it's a consolidated granular soil for the at-rest soil calculations there. And we've got the Ka, which is the active pressure, and the Kp, which is the passive pressure. They're both calculated. So we also see if it's a cantilevered wall, the Ka on the heel side is going to be used, and then the Kp, the passive, is going to be used on the toe side. If it's a propped wall, we're going to be using the at-rest for both heel and toe. So it depends on what we choose for whether we use a supported wall or a non-supported wall. If you want, you can put your own K value in there. We'll see that if you leave it blank, when we go to the input, it will calculate it based on these two, backfill and coefficient of internal friction. So that's going to be your soil pressure, and we're automatically going to calculate that and put it onto your wall, and we'll see the loading diagram in a second here. But the loading that we do also, we can also input calculated loads. So not only are we going to put soil loads, but we can actually put some other loads in there. And then what we are going to do is categorize those into different types of loading. So for what we see here is dead load is going to be categorized for our weight of our concrete and our soil. We've got live load, which is going to be our surcharge above that, above the retaining wall there. We also have hydrostatic loads. Any lateral pressure or hydrostatic loads are going to go right into the hydrostatic load category. That might be a new one for you. We've created a new load combination set so that the basic, the generic load combinations, the defaults that come out, you'll see I've also now included this HL for hydrostatic load. So we're always including that. We also note, something to note is that all these loadings are going to be put on a per foot basis. So when we look at the model there and we look at the retaining wall, we're going to be seeing things per foot. If we look at this a little closer here, when we do sloped backfill, that's kind of an important thing to note when we break into loads there for sloping. The force is going to be broken into the cosine applied horizontally as a pressure, and then we're also going to break in the vertical loads into the sine, and that's going to be lumped onto the top of that wall. So this picture shows us how we have a backfill, and now that backfill gets reduced into two different types of forces, in the sine and the cosine. So we're going to apply those right directly to the wall. So what we're going to be doing, just like we always in RISAFoundation, we're using category designs with dead load, live load, and hydrostatic load. And we'll see that in practice in a second. The other thing that we will talk about here is some of the modeling that we're going to be doing. So when we model these loads, and we'll see that we're going to want to model these loads directly on the wall center line. Now this is important to note if this is a three-dimensional. So in RISAFoundation, we're typically looking at more two-dimensional. This retaining wall is kind of our first time where we're really in 3 dimensions. So we've got to see that this gray line here is what we call the center line of the wall, which is really the base of the wall. And what we're going to do is when we apply loads to that, that's where we're going to be applying it along the base there. So the point loads and the line loads can be applied along this base, and we can apply loads. And what they're going to be doing is they're going to be actually being applied. So we would draw this red line here. This would be as if we were drawing a line load on it. And then what happens in display, it actually gets carried to the top of the wall. So even though they're drawn at that base, we're going to carry all those loads directly to the top of the wall so that that stem wall gets loaded. So we can see here kind of the different distribution of load there. And what else we do is we're going to start talking about some of the design checks we do on this wall, on this retaining wall. So overturning is one of the big things that we do in this design wall, and we check this overturning based on the extreme edge fiber of that toe right there. So right where that red dot is, that's where we're checking our overturning. And each section is taken into account. So we see here that we've got the concrete weight for the stem wall, the footing, if we have a key, the soil weight, any of these soil weights are going to be added up, the surcharge loading, if there's any surcharge loading above there, the lateral soil pressure is going to be counted for, and any of the water pressure. So all of those things are going to be accounted for. And these sections are going to be added up together, and they're on either side are going to be the resisting moment or the overturning moment. So we can see kind of from this calculation here, we're going to make a ratio of resisting moment over the moment of overturning. So all of these are added up, summed together. And then we see that the ratio of calculation is shown here for the safety factor, is then checked against that safety factor to create what we have a unity check. So OTUC will be something we'll see, and that will be overturning unity check. And what we're doing is we're grabbing that safety factor right out of your load combinations. So you can see there's a safety factor listed right there, and this is just a sample of what our load combination might look like, and we can see that 1.5. So that's really what's going to determine this unity check. We also are going to see in the results there, if we look at some of the results of this retaining wall, we have a spreadsheet that comes through, and we see here on the right side of the spreadsheet we have the overturning unity check. It gives us the load combination that governed, and then the maximum overturning right there listed per foot, like I mentioned. So we're going to do this whole check here. for you, only on the ones that are on retaining walls that are cantilevered. So propped ones, we're not going to do overturning check because, of course, they are propped, so there's not really any overturning or any, they are supported by something at their top. And then for sloped backfills, the vertical component of the hydrostatic load is also going to be included, so that would be something additional in there. So you can see that. The next check we do kind of goes hand in hand with overturning is sliding. So for sliding, what we do is we check the sliding at the extreme bottom fiber of the footing. So if you do have a shear key, you're going to see that that little red line here is going to show us that shear key. That's the bottommost as well. But if you don't, then it's just going to be the full bottom of the footing that's going to be checked for sliding. So what we see here is that we're going to do, this equation here shows us what the sliding resistance is, and that's equal to the friction resistance plus the passive soil. They're both accounted for in that equation. And what those friction resistance, we have some equations that show here what those friction resistance is. The total weight is going to be the total downward force that's acting on our soil. So our soil, our concrete, our surcharge forces, that's our total weight. And we're going to take that for the friction resistance. For the passive soil here, we can see we are going to be using our coefficient of friction there, and that's going to be listed right directly inside of our global parameters. The next thing here, let's just quickly, this is just exactly like the overturning. So we see that we take the overturning, we did a unity check just like that. We also do that here in sliding. We take whatever the sliding resistance is, divide that by what the sliding force is. We find what that value is, and then we compare that to the safety factor. Again, that safety factor is coming right off of the load combination spreadsheet. So we're using these checks to complete the sliding check. We also check the concrete shear check. So we can see here that the foundation, RISAFoundation, is going to check the concrete and the stem wall and how that's going to shear. So the distance D is defined as a common definition for D is going to be taken here based on a couple different things. If you're a cantilever, we have two Ds here listed on this diagram. And if you're a cantilevered wall, we're going to check the D based on the top of the footing. We're going to find that distance D there and check the shear for you. If we're a propped wall, we're going to actually use the top there, the top of the actual retaining wall, stem wall. And we're going to use a distance D to check that. And we're using the ACI equation listed here for you to check this distance here. We also do a shear friction check. Now, shear friction check is something that's required if the base of the wall if the stem wall is not poured monolithically to the footing, and so what we do is we assume that the dowels from the footing are going to match the vertical reinforcement that we have in the wall. So you can see that's kind of how we lined it up in this diagram, and we're going to do a check on that. Based on what you say, right here, if you say that the wall or footing is continually, if it's actually roughly attached or if it's not monolithically attached there. So we're going to tell the program yes or no, and then we're going to say rough or smooth, and based on the rough or smooth there, we're going to change some of the factors that go into calculating that value, the shear friction. So you can see it's going to adjust that based on what you've got listed. This is now here, this is the first time we looked at this retaining wall factors, but what this is the retaining wall design rules. We'll go into a little bit more detail seeing how we define this, but it's really just a yes-no question that's going to ask you. So the friction shear check is also checked in this for the stem wall going down. The other thing we do is we're checking all of the footings. So there's a lot of different checks for the footings, and the footing checks here are going to be a couple things. Starting out, we're going to do is check the maximum soil pressure. So that's based on the moment and axial force at the center line of the footing at the base. And the soil and the surcharge here are going to be considered in this as well. So we're basically assuming that this is like a cantilever coming off of those, and we're going to find the forces based on the moment and axial forces. We've got a pretty good example if you wanted to hand calc this. I didn't want to spend all of our time hand calcing it, but we have a good example in the help on if you wanted to try to hand calc this Q max and Q min to find that maximum soil pressure. But we'll also see this described in our load diagrams. Okay, so we're going to also go from there. We're going to say the other check we do is the flexural design. The flexural design of this heel portion here we can see is designed as a cantilevered beam as well from the face of the retaining wall. The RISAFoundation considers the moment at the face of the heel, of both the heel and the toe, and then we're going to design for the worst case of those load combinations. And we're going to tell you what load combination governed for that. The flexural reinforcement and the shrinkage and temperature reinforcement is going to do the minimum steel requirements as per the code. So we'll see there will be cases where it's going to tell us that that is not meeting the minimum. So these pictures kind of show us here on the left side shows us kind of a lightly axially loaded, and on the right side is kind of a much more heavy loaded axially, kind of just a nice description of it deflecting. We also check the shear checks. The shear checks there are going to be done for the footing, and this is the same kind of check we were looking at before, sort of in a different direction with that D distance away from the edge of the footing there. So you see that we go, the program's going to check that in each direction based on what type of loading is going to be got in this footing. So you can see depending on which way is going to be the critical direction, and we're going to find that appropriate location for you based on that. So the shear, we've got sort of a rundown of all the different checks, and now I'd like to sort of take a look at the program directly. So let's see here, kind of jump in and see RISAFoundation in action. So let's see, I'm going to open up RISAFoundation. And like I mentioned, this is RISAFoundation 4.0, so brand new feature inside of there. You'll see some of the different things that we've got: retaining wall definitions. Let's open up that. So on my data entry toolbar, I have retaining wall definitions. I'm going to sort of scroll over here. My screen's a little bit minimized, so it's harder to minimize this a little bit. So hopefully everybody can see my whole screen. I've shrunk it down, so we might have to manipulate it just a bit. But starting out with RISAFoundation, you've got some basic retaining wall rules as kind of or definitions. Just like the other types of materials, you have pile definitions, footing definitions. Retaining walls have their own definitions. And it's spreadsheet based like the other ones are, but what I sort of like to use as this newer feature we added is a much more graphical interface. And the way you get to that graphical interface is you see this little red arrow that's still highlighted whenever you are on the label. You want to just click on that little red arrow and it pops open to a retaining wall definition editor. So this is all the same information that you would have seen if you were looking at the spreadsheet. It's just much more graphical and easier for us to see. So I really prefer using this type of an input. And what we're doing here is we're just laying out the rules of the wall that we're about to draw in here in RISAFoundation. So first of all, we have some options that like we talked about a little bit. We can change the thickness of the wall. I'm going to leave 18 inches as my thickness. If I want to keep it propped or not propped, and this one I'm going to use as a cantilevered wall. So I just say no to the propped wall, so it will assume that there is no support at that top level. The H wall, the height of the wall, I'm going to adjust that to be maybe 12 feet, and it's going to then adjust the wall height there for me. The toe length, now that's going to be that distance on the top and on the toe there from the edge of the wall, okay, not from the center line. So that's going to be, actually leave that as 3. Now I can add a key to this wall, and I think I will just to help demonstrate what the key will look like. So the key, I'm going to match my width for my key to be 18 inches. I can offset that key from a little distance there. I'm going to leave it as in the center line, so it'll be actually in line. We're going to see this drawing is going to stay static, but when we look at the results and we look at our detail report, it's going to all look to scale. So I've got my heel length, as 4 feet. I'm going to leave that. I'm going to give some depth to this key. I'm going to say it's going to be 24 inches. And I'm going to give my dowel maybe 1 dowel there. Actually, it won't matter. I'm going to say I'm going to actually say it is not poured monolithically, and it's going to be rough there. I can also restrain that. If I restrain the footing, then all of this sort of kind of goes away because we're restraining that footing. So you might have restrained footing if something else is supporting it, with a slab coming in that's helping to restrain it. But I'm going to say it's not restrained. This is a freestanding cantilevered retaining wall. My footing thickness is going to be 12 inches. And I'm going to leave my saturated there as 6. Now I want my height of my wall is 12, and I'm going to say the soil is going to be at the same height, so 12 on the other side as well. So I'm going to leave all those to be the same. So I've got that laid out. I'm going to jump over to the Soil tab, and I can see in the Soil tab I have some information in here. Starting at my toe depth is at 2 right now. I'm going to increase that just a little to drop it down to 3 feet. And I can either put a K in. Now, one thing I should mention is you can see that what's happening is just like we have this description at the bottom, whenever I'm in a field, there's a description that's happening right below. So if for any chance you say, hey, what was that was on that screen? I don't remember what happened during that webinar. What was she talking about? You click in the box, and then it says down here exactly what you're sitting on. So it tells you what you should be doing there. And what's nice is there's some clues, like K-lat. Right there it tells us that's the earth pressure coefficient. And it tells us there that we can leave that blank. So it's going to calculate it for us. So I'm going to leave that blank, but 0.14 is a little high, so I'm going to adjust that to 0.11. And I'm going to leave 30 as my angle. I'm also going to change the saturated. It's a little high as well. I'm going to switch it down to maybe 125. And I'm going to also adjust the heel side there to be maybe 0.11. Now, I'm going to give myself some angle, so you're going to see that how the angle works. I'm going to say maybe 10% is on my alpha angle there, which is my backfill. Okay, and then I'm also going to just leave here my surcharge so we get to see a lot of the loads happening throughout this one. I'm going to go to the rebar tab. Now the rebar tab, you can adjust all of your rebar information in here. And let's start by kind of filling out some stuff here. Since this is pretty highly loaded with my soil, I'm going to leave each face. I could adjust that to single face if I want, but I am going to say each face there. So I'm going to leave it as both because I don't know that it will work with one layer of reinforcement. I can tell the program vertical, outer bars, vertical or horizontal. That's really going to affect the D value. So it's up to you however you typically detail, but I'll leave that as the vertical. Interior cover is a little high for 3. I'm going to adjust that down to 2. And I'm going to say maybe my horizontal bars are going to be 5 at 18. And we'll say, let's see, exterior bars are set. Let's see, I'm going to switch everything to be maybe 7s so everything matches 7. This is all based on the top, the stem wall. Now the bottom portion here is going to be based on for the footing. So I'm going to come down here and just adjust things. Since you typically design, similar reinforcement, I'm going to just make this 7 on the footing so that, there's no mistakes happening in the field. I'm going to switch everything to be matching number 5s and number 7s everywhere. And I'm going to kind of go through here and switch everybody to be number 7s. So you'll see you can define some of the spacings so that it's going to design the spacings on this footing from minimum to maximum. You can change some of the covers, obviously, there. We can adjust the cover to be maybe a 2. We can see kind of lay out all of the different reinforcement. We can say, once we've got it all put in here, I can say OK. And now if I had to make a quick change, I would definitely want to just pop back in here and adjust these values like this. This might be an easier way, but for me, I really am much more graphical. I like to very much look at the picture and see what's happening there. So it's just as easy to click the button either way. It's really your decision. So what we'll do now is we'll start loading. Let's start building this model. This is just a single retaining wall that I want to build. We'll build a bigger model in just a couple minutes, but I really want to see how this single wall works and what we can glean off of just a single wall. So when you're in RISAFoundation, you're looking at a plan view. So it's as if we're looking down on the model. So when I start to draw this retaining wall, we can see there's a Draw Modify Retaining Wall icon right there, and I can click on that. And in here, I can tell the program any sort of information. I can switch to 4,000 normal weight. Might be a nice weight there. I defined retaining wall 1, a definition right now. But say if I wanted just to start a new one, I could just jump in with a new design rule right there. And it'll create retaining wall 3, or we can title it a little bit more informative. I'm going to push cancel, and I'm still just going to use that 1 since we already spent the work to do that. And I'm going to say apply. So now I'm just going to draw this on my plan view. I can draw it anywhere. I'm just going to draw myself a nice 30-foot long wall. And I can, keep drawing and go from there. But we'll just take a look at this single wall for now. So if we look at this down on the plan view, we sort of just see it as our footings and our heels. And there is now a common local axis to this wall. So if you want to see the local axis, you can sort of see the direction of that wall. I'm just in my plot options, I can see the local axis. and I can see that Z is pointing in that one direction. Now, if by accident that wasn't the right direction, I could flip-flop this wall. Sometimes you might end up having to switch things around. I could use this out-of-plane flip, and it will just sort of adjust that for the heel versus the toe version side of my wall, excuse me. But what I'm going to do here is I'm going to leave it the way it was, so I just reversed it. And I'm going to see here, I'm going to look at it as an isometric view. The isometric view really helps you see it. Helps you see which way the walls got its soil on one side versus the wall having the reinforcement, interior versus exterior, excuse me. And so we can kind of just see this rendered a couple times. You can see we've got our key in there. We've got all sorts of abilities to sort of render this and look at it in different ways. I'm going to take our local axis off so we don't have to see that while we're drawing. Okay, so we can see show retaining wall, but no local axis. There we go. Okay, so now I want to look at this model back in plan view for a second here. And this is actually a little bit, sorry, this is skewed the wrong way because I do want to add some loads and it's coming in the wrong direction. So I'm going to flip-flop it, even though I said it wasn't. I'm going to actually do that. So I'm going to flip-flop it so this is the interior portion of our model. So maybe our basement wall is inside of here. So I'm going to look at this back in plan view, and I can do sort of a lot of different things with modeling for the loads. So the one load I want to do is I'm going to define maybe some dead load. So I'm going to go to here and apply some dead load, and I'm just going to put some fictitious loads on here, maybe 1 kip per running foot, and I'm going to just draw that. Now when I'm drawing it, I want to make sure I'm drawing this on the wall. And just like we saw when I showed this slide, I'm going to draw it from the center line of that point to the other center line of the other edge of that wall. I can go shorter, but what I'm going to do is going to go the entire thing. Now when I finish drawing, you see it pops right to the top of the wall. Okay, so it needs to be drawn on the center line. Now I can draw a load over here on the edge, but that's not going to be applied to the wall. That's going to be applied to, nowhere in space. I could put a grade beam underneath it, or I could put some footing, something down there, a slab, but that is not going to be applied to the wall. If you want it applied to the wall, you got to put it right on top of that center line, that gray darkened line. Now I also can do, I'm going to do maybe some point loads. So I can come in here and apply some point loads. And the point loads I can do all sorts of, just maybe again another fictitious 1 kip in, positive direction because that's downward. And I'm going to say that's also a dead load, and I can apply that anywhere. Now I need something to click to, so even though it's going to display at the top, I'm going to want to sort of click to the bottom on my grid. So I can see it as I click down here, it pops to the top. And I'm going to go to plan because plan's a little bit easier for us to draw like this. So I'm going to go ahead and maybe put in a couple different point loads in this wall. And these might be, I don't know, they're going to be your columns coming down on your wall, something like that. So I'm going to apply those as I see. I've just sort of sprinkled them around. And I see, as I look at it again, those point loads are running directly through our wall. The other thing you can do is apply some point loads maybe in the wind direction, wind load point loads, okay? Again, that's probably going to be, if we look at our axis, that's going to be in the Z direction, okay? So I'm going to say that these point loads are going to be in the Z direction. And probably most typically coming in at the same spots as our columns, so I'm going to just tie them right to my columns. They don't have to be, it could be their own, but I'm going to put them right at the same place. Okay, so you can sort of see as you draw that, that I've got my loading in place. Oops, you know what? I didn't do that right. Let me redo that 1 sec. I put that in all in the wrong load combination. So let me put that all in the wind combination, sorry. And we'll just see that there. We'll get a little bit better results if we paid attention to our load categories. Okay, so we've got our dead loads, we've got our wind loads in place, and that's probably what I'll just keep for now, just dead loads and wind loads. And we're just to sort of demonstrate. Now the other thing to just explain a little bit about how things tie in. So you're not going to have connectivity between members if I try to draw a beam, okay? So say we had drawn that point load, those line loads there, and I draw a grade beam right sort of in line with this. So if we look at this rendered, this grade beam is in line with the footing of this. these are independent. So, and just like the loading goes, if you are not in the center line of that, it's not going to connect to the retaining wall. Okay, so retaining walls are on their own. They're not going to connect to the grade beam. They're not going to connect to footings. They're not going to connect to like a single spread footing. They're not going to connect to a slab. They are their own entity, and they're getting their own loads. Okay, so it's important to note that you tie things together. It's going to be just sort of on its own. So we've got this wall already started. I'm going to go into the load combinations. And as I mentioned here, the standard default load combinations have now added for this hydrostatic load, which is a new one. So if I just run this right now, it's going to account for everything like the self-weight, all of our hydrostatic load, pressure behind that wall. Everything is going to be there. The only piece that's not going to be there is our wind load. So let's go ahead and make sure we add some load combinations to account for that. So I'm going to say wind load there. I'm going to apply that wind load and just say generate, and they'll go ahead and create wind load combinations. So a lot of these are not needed. I'm just going to uncheck them and say only solve the ones that I care about. So we'll maybe solve some of the wind load ones. And we've got wind load on different directions here. So I'm going to solve this model now, and we'll see some of the information we get once we do have a solution present. So we get the results toolbar popped up just like we always would in any type of structure. And then there we can see I'm going to open up the retaining wall results. And I've got a spreadsheet. Close this and see. The spreadsheet breaks it down for us. So it tells us what happened in the footing. This is the heel flexural unity check with the load combination that governed. It tells us the toe unity check. It tells us the shear, and for both the toe and the heel. Okay, so we get all those checks there for the footing. We also kind of break down here the wall. So we see the unity checks for the interior and exterior of the wall. We see capacities. It lists out exactly what the capacity of this wall is for the toe, the heel information. We jump to the geometry. This is going to just really echo back what we put in. So we just know that the program is understanding, okay, we did a 12-inch wall. Sometimes you have an 12-foot wall, an error in your input. So it's always good to see that back in the output. So you're, oh, okay, that's why that didn't work, because I didn't set that right, something like that. So I do like to see the geometry nicely on the output. We see the steel bars that were placed there, and then we see stability. Now in this model here, we're looking at this, we see that the sliding check is not quite right there. So I've got, currently it's got 1.334 for my sliding. So I might want to see this a little bit more detail, and I like the spreadsheets. They're really great for kind of a one-off, okay, and what's nice is it's in red, so I can see that quickly, that there's something wrong. I can pop through those. But what I like to do is look at the detail report. You can just click on the top here, detail report for current item. And now this gives us a lot more idea of what's going on in this model. So we see the sketch of all the reinforcement. This is a great sketch showing us all of the vertical bars, the horizontal bars. I like that we see now the water table. We see that the water level is. We see actually how far I dropped that. Oh, is that 3 feet? Yes, that looks like it's 3 feet in the interior. Now, again, it reminds us that the 4 foot was the heel, the toe is the 3 feet. We see, okay, that's exactly what I was thinking. Maybe I want that to be 4 and 4. So I can then go back and adjust that. But this is a great graphical representation of what we modeled. So we get to see that a little bit better, kind of error checking ourselves. And then even for construction to understand what type of reinforcements there. And below that, we get our loading diagram. So this starts to break down great tools for seeing how this load was applied, what was the forces that were downward. This is the service load combination that we're looking at. If we look at the strength, we're going to see it adjust. So it's a great, you can pop through all the different load combinations that we checked, and you can see the different, which one's controlled. So maybe the strength is the one that we might want to look at a little farther. And as I scroll down, I can see the different breakdown of all the different forces on this. So as we scroll down below that, I also get sort of similar to all of our RISA software where we see what was the reinforcement and listed it out, tells us all of the inputs. We see our heights, our concrete, gives us a lot of the input, kind of what we also call this an echo report of what's happening. We also, let's see, I'm going to open this up a little bit. We can see our coefficients here and how they were calculated, which is nice, for the active and the passive. And let's scroll down below that. Our moment and shear and axial diagrams. Now again, notice this is per foot. So you're seeing an axial per foot, shear per foot, and then a moment per foot, right? So you've got that. So what you want to note is that if you are doing something that has high stress risers, so we're taking all of these loads and applying them to the entire wall. So maybe that one of those point loads was real high. What we might want to do, since maybe 30 feet is an over-exaggeration, and it would be a sort of a very spread out load to say, okay, everything is taking that. Maybe we had a 50 kip load, something really high, something coming in, and we really wanted just to focus on that design, carrying that well in that one area and not spreading it out. What you might do is just draw segments of walls, pieces that break it up a little bit so you can really get those stress risers inside of the wall. Otherwise, we're just really going to be taking that whole wall on an average. So let me grab that. So which is typical for concrete, but if you are looking for it to kind of spike, you might need to break up your wall. So we see those detail reports, we see the diagrams right there. On the right side there, you see the breakdown of the axial loads and the bending loads. Now there are some thresholds. So if their loads don't get above a certain limit there, you're going to see these zero out. So it's something not to get nervous about, but definitely you can see, okay, there's a threshold that's happening. And so what we're doing is we're taking that axial, and that's not governing, so it's kind of throwing out the door there. But it's because it didn't hit the threshold value. So we scroll down below that. And it looks like here I've got my shear details telling me which unity check was my max there. I've got the full area steel provided. This is kind of a nice check for why things that with the area steel provided might be, we have a big note telling us it didn't hit minimums. And so we can say, okay, we need to hit minimums, so we can kind of look through and find out why. So right now our horizontal bars are not meeting minimums, so we might want to up that a little bit. And as we scroll down below that, I can see my footing design listed out, similar to what we might imagine in a footing. So we've got the toe design is listed out here with our area steel, the heel. It also does the overturning check like we mentioned for the service, and for sliding is for the service. Good thing to note, those are for the service combination, so make sure you pay attention to which is your service. And scroll down below that, and we see our soil bearing check, and it's giving us listed that there for what was the maximum bearing and the allowable bearing. So we can kind of upsize this a little bit to work with it. So we see we're having some sliding problems, and we have some horizontal bars that we need to meet minimums. So you can do kind of several different things, but I really, as I mentioned, I like to go back in and just adjust it graphically. So I hit the retaining wall rule, and I pop back into the rebar. Okay, you can see I have horizontal bars number 5 at 18. What I might do is just try to adjust that to 12, see if that can get me there. The other thing here is we've got some sliding issues. So maybe I'll drop the depth of this toe a little bit. Let's see if we can get down to 3.5 feet and if that will work for us. So I'm going to say okay, and then I'm going to run this model one more time. And I'm just going to pop into that detail report. I can do the detail report just by clicking on there and coming in. And let's see, let's scroll down a little bit and see if we got rid of that. So we did get rid of that area steel message. That's nice. So we're meeting all the minimums. And as I scroll down, I'm still not quite hitting my minimums for my sliding check. So I might go ahead and let's see, I can go back into my retaining wall. Maybe one more effort to see if we can upsize that. Let's see, we've got our toe length. Maybe we adjust our toe, maybe make it a little bit bigger. Maybe we drop our key a little bit and see if that helps us. So we've got, say all those, and we can say okay. You see it adjusted the graphics nice for us, so we can see they're now even on both sides. And we can come back in here and take a look if that works. We're still not quite there, so we might want to do a little bit more work to that. But I'm going to leave it for now so we can move on to the next model. So you've got sort of this idea of what's happening in this one single wall, and you can see how this single wall might operate. What I'd like to do is incorporate this into a full building model. So I'm going to jump into RISAFloor. So I'm going to close out on this, and I'm going to say, I'm not going to see that. We'll jump into another model, and I'm going to open up RISAFloor. So if you're not familiar with RISAFloor, this is going to be a full building design tool that you can lay out your full building. I'm going to be doing all my gravity loading in here, and I'm going to carry that gravity loads down the building. So hang on just a sec while this opens up. Again, you'll notice this is version 6.0. This is a brand new version, released just a little while ago. And I built this model sort of a sample model. Let's look at it in a full model view. So it's got some interesting geometry. I just sort of something smaller, but I'd like to just sort of show you some of the different pieces on this one. It's just a steel building. I put some concrete shear walls in here. When I was in design, what I a lot of times did was I built the basement walls were a lot of times used as my shear walls, and then my upper floors kind of carried through in a smaller geometry. Just portions of that wall were used for lateral. I sprinkled in some moment and shear frames in here. Maybe you just stick with one type of material, but I figured I'd like to sort of demonstrate a little bit of everything in here, and then sort of get up to. So this is just 2 stories, and then I did put a basement level in there. So this is ground floor. This is our below grade level. And if I run through solution, I'm going to just solve it one more time. And I'm going to see here, solve this model. It's just going to be giving me design. Now what you'll note is that anything red is our lateral members. Anything that is blue is our gravity members. So in RISAFloor, we're carrying loads down the gravity system, and we're designing the all the gravity system in here. So lateral is being designed for gravity as well, but you'll also see that we're optimizing each member. It's running through a solution, trying to find the best solution for each floor and carrying those loads down the building. We're assuming a diaphragm that runs around the edge. So I have a deck and a diaphragm edge here. And I see that each member got designed. This was sort of a joist system that I built with some of these. And we see this is also a feature that was added in the newer versions. About a couple versions ago, it's concrete shear walls. You can design these concrete shear walls, and then now we can take that all the way into RISAFoundation for design. So I'm going to take just the lateral system here from RISAFloor into RISA-3D. So using the director button, I click on the RISA-3D button up here, and it takes over to RISA-3D. I see that I have ASE 7-2010. That's a newer code that got added, and I can scroll down and see some of the wind loads that are calculated on my building. I'm going to say OK, and this is some of the seismic loads that were calculated in my building. So I can see all of these are applied to my building. I'm going to say OK, and I'm going to jump over here. So now just the lateral portion of the model is here. And I'm going to say, let's get rid of some of these nodes so we don't get cluttered. And what you'll see is I've got those basement walls there are being used for lateral design. So I'm carrying the in-plane loads here to design this lateral for the lateral system. I've carried some of these to multiple stories, but mostly it's just my basement. And then I'm going to solve this model. Okay, I'm going to run through an envelope solution and just solve it. And it's now distributing all of my lateral loads into this lateral system. So I can show you after we've run solution. It'll just take a second here. But what we do is that we have diaphragms designed, rigid diaphragms around here. So what I'm doing is carrying all of my loads directly through my diaphragm. And now this is all going to go over into RISAFoundation, which is a really nice way to get a lot of loads into RISAFoundation. Sometimes it's intimidating how much loads are going to go over there, so we can see that. But you can see how much load is getting accounted for from the gravity system. This is just my dead load. But we also have our wind loads in the X direction applied to each diaphragm level. I can show you those diaphragms there so you can see a little bit better. We've got the wind loads. We've got seismic loads. All of those are being applied in our model. So earthquake loads in the X direction, and we can see all of that being dropped right into a point load that gets distributed based on the rigidity of those rigid diaphragms there and as they get distributed to the members. So then I take this model over to RISAFoundation. So using the same director button, I go over to RISAFoundation. And as you see, the model is then carrying all of these loads over. So I've started this model ahead of time just because it was a lot easier for us to start there. But I want to show you kind of what we're looking at in this model. So if we look at this in isometric view, first of all, I'm going to take all these loads off because it can be, like I said, can be a lot of loads to look at. So we look at it, kind of scroll in a little bit. What I did is I drew in a retaining wall around the edge there. Now this retaining wall is for the out-of-plane design in RISAFoundation. So I did draw it in here in RISAFoundation. If I look at in plan view, just like we did in a single wall, you just draw that in, and I drew it right on top of where I had some point loads coming from those walls that we modeled as lateral walls. And then I put in my footings all around. And now I have some footings that are defined, a couple different types of footings. I put some gravity footings. I also did some lateral footings, so wherever I have a lateral frame, I might design it a little differently than if I had it just for gravity. I also have some pile caps. So I put some pile caps described right here. And then I drew a slab on top of this area here. So I'm drawing a slab with my pedestals. So if I'm doing more of a combined footing type of structure over here with a thickened slab. So I've got all of that in place. But what's nice when using RISAFloor and RISA-3D into RISAFoundation, you can link RISA-3D by itself into RISAFoundation, or you can link RISAFloor, RISA-3D, and come over here into RISAFoundation, and we've got all the loads. So you can see to do this by hand would be kind of a tedious job. But if you link them all together, you can bring all those loads in the different directions coming right across. So this is, you can see all the different wall elements are carrying those loads right in there. You've got the point loads from all of the different structures that were coming in. We had kind of a frame, a little radial frame coming in here. This is all the gravity loads. Those are just the gravity dead and live loads. We also are going to see that we're going to be able to see all the wind loads in the X direction, for example. Only for the lateral portions we're seeing those wind loads. We're seeing in the Z direction, all distributed to the joints that are going to be accounting for them for the foundation, as well as earthquake. No, we don't have any of those, but we have earthquake in just the ELX there, and I have ELZ direction. So all of that comes across, and it's nice because it's categorized. So it's all there as the point loads listed out per category that came in from RISA-3D and RISAFloor. So when I do this type of design in here, I can solve the model. I can, let me take a look at my load combinations real quick. I've laid out a lot of different load combinations. I went through and I created a ton of different load combinations, and I kind of went through them and picked out which ones were governing just so I save on time a little bit. But you can run all those load combinations, and what it does is in RISAFoundation, it's an envelope solution. It's a little different than RISA-3D by itself. You have a choice between an envelope and a batch solution, and then it gives you results based on what you chose there, or a single solution. And in concrete design, you really always need to do an envelope solution. You take each single combination, you put it all together, and you get your envelope solution, and concrete and reinforcements designed based on that. So you really don't get a choice, and we can see it's just going to run through these different combinations that I selected. What we're doing is sometimes you can see you're breaking this into all the point loads. So in a larger model, it may take a second or two, but it runs through all those point loads that came in there from RISA-3D. And we run the model and get all of our solutions. So, and it also tells us here what it's doing at that point. So it's designing the footings, it's designing the pile caps, and we get information on that. Now, the results here are going to be similar to the results that we saw when we were looking at a single combination. Just a little bit more spreadsheet might help to understand it a little bit better since we're looking at groups of walls. We can look here now and seeing what's happening on each wall. Okay, we can look at the load combinations, and then you can really start designing this. Okay, these are pretty low, these unity checks. So either I might have over-designed this wall thickness. I think my wall thickness on this one, let's look at our geometry, is 18 inches thick. So I probably put a lot of reinforcement in this one just to meet minimums, and it might just be too much since all of my different categories, they're all small, real small for my unity checks. So maybe I want to start sizing things down. I don't need to use that much. I can also look at here the number of the steel that I use. So number 8s and number 7s, and it looks like I wasn't real consistent on the number of bars I used, so maybe I dropped things down to number 7s to try to get them a little bit more equivalent. And it looks like I am hitting minimum spacings. 18 inches is typically the minimums, so I might be able to size this bar down. I'm going to also look at the stability checks here. So right now I'm not checking for sliding. So let's just review this for a second and kind of understand why that happened. It looks like I told the program I was propped. Now that would make sense for this type of wall because what's happening in this building is we are assuming that at the top of that wall we are having a rigid diaphragm frame in. Okay, this was a model that came from RISAFloor and came to RISA-3D, and there was rigid diaphragms designed in there. So that wouldn't be a bad assumption to call it propped, although you saw the unity check was pretty low. So what you might want to do is just switch that to no propped, and just see how badly that might affect it. So we can say, yes, it is monolithically poured, but it's not propped. I want to sort of be a little bit more conservative, not use the top so it's propped, and see really if that's going to, how that affects our model. And you can rerun that. But what is important to note is that when you do have it propped, you're not going to get that sliding, you're not going to get that overturning, and that would make sense because it is supported. So we run through that combination, these combinations one more time. We can see that a little bit farther. Now, one thing to note, if you aren't familiar with RISAFoundations, some of the newer versions, we have the pile caps in there, and I put those in so you can see some of the newer features. You can always have done footings, slabs. You can do the pedestal design there. So you can put a pedestal right on top of a slab, and we can see how that pedestal is punching shear checks, and we can check overturning on that slab as well, and we can see a little different information on that. So we're almost done with solution here in a sec, and we're just designing the footings. And now let's see how well this does. So we go over to our footings, and we're still pretty good. Everything is looking pretty good in our footing. Our unity checks are pretty low. If we go over to the wall itself, now this is a little bit more in line. So probably when I first built this, I was assuming it might not be propped because I'm a lot more closer to the line on here, at least on my interior. My exterior probably could still be dropped down in size for that reinforcement. I'm going to go over to my geometry and my steel. Okay, so we didn't adjust our steel, but making sure that things are, okay, so it looks like sliding is right on the line. So 9.9 we've got there, so it looks like I'm just quite making it there. So it still would be something to consider if you were doing that as a retaining wall that was cantilevered versus propped. So I'm going to jump back into my retaining wall here. I'm going to open up my detail report real quick. So you'll see it's very similar to what we had in this previous wall. This one here we've got listed just like we saw before, giving us a breakdown of the loads. This is showing us here there's no forces in that direction. We're not propped. And I scroll down here. This would be where we, again, sort of look through and to make sure we're hitting our code check information. We see 0.9, everything's looking okay. And then we scroll down below that, and we see that sliding is really close to the line. So maybe we worry about that, but again, this was the cantilevered portion of it, so we might not be so worried. We can also see any of the results. I might want to just point out here the safety factors for. This is for our slabs. This is a newer feature. You can see that you can now check your overturning checks and your sliding checks for that. And we're taking the governing overturning moment versus the governing stabilizing moment there for both directions, X and Z. And then it gives you the ratios there, and then the sliding checks there. So you can see that what the governing is there versus what the allowables are. So those are newer. You've also as I mentioned, the pile caps. If you're not familiar with the pile caps, I did put some pile caps in. It's designing this pile cap. As you can see, the piles are defined. This is all based on our pile information that I've got in my just like I have a pile, a retaining wall definition, I have a pile cap definitions where I can tell the program a little bit more about how those piles are, if they're round, if they're square, how they're framing into this pile cap, and it designs the reinforcement there. Now for the pile caps here, I tell the program what that pile capacity is, so I just give it a list of what it can take for its governing axial, and then we tell the program what kind of axial capacity it has, and then same thing for if it's going to take any compression force, if it's going to take any shear force there. I can tell the program specifically what the pile is, and then below there it's going to design that cap. And those special checks you get punching shear, you get pedestal punching shear, similar to what you would have for a footing. So it looks like we're overlapping a little bit here with our groupings. That we scroll down below. This is sort of our maybe our one extra little check here. One-way deep beam shear check would be more of a pile cap check that is beyond what we would have in a footing, and then you can get the pedestal design there, and that's more like a footing too. So you can see kind of a layout there, just like we see also the footings inside of our RISAFoundation. So that kind of wraps up. This model brings us kind of full round with any type of elements that you would have in RISAFoundation. I think I didn't put grade beams in, but that would be the only one that would be out of this model. So it gives you a good idea of what this is. And after the presentation, we will be posting this model as well as my single shear wall model, single retaining wall model on our website. So if you're interested in taking a look and playing around with it, you can open that with the demonstration version too if you don't have the other programs. It might be nice to sort of see how they interact and work around with that. So definitely take a look at that and feel free to ask us questions. But at this time, I'm going to turn this, let's see here. I think we just quick notes on housekeeping. I'd like to just mention additional resources. So I mentioned a lot of new features, and we do have our release notes. We also do focus on new features in our risanews.com website. So that's kind of a website that's off of our website, and you can see articles on basically everything. We try to pull in things from technical support. We try to pull things from common questions. We do a lot from the new features so that we make sure everybody is kind of educated on what's new in the program. Again, if you can always contact us at support@risa.com, and then we have some users guides as well available on our website too. So if you ever want to work with the program and learn more, you can use the users guides there too. Right now, I'll turn it back to Amber, and I'll conclude my portion. Thank you very much for attending.